Okay, so what I'm going to talk about today is some applications of what we've been seeing, especially in this last chapter, to image and signal processing, which are sort of two areas that come up a lot in my own work. It's just why I can make a lecture about them. Let's see. Oh, of course I can't change the slides. There we go. Okay, so first is signals processing. Are in some ways the same because images are signals. But when you talk about signals, usually you're talking about a time series, which is just a function that maps some time points t to, a function, which is usually some sort of physical measurement. So, some of the very, very many examples of time series that you might care about would be wave heights that you measure from a buoy, like over time. You have a sensor that's measuring the height of the waves, and then what you get at the end is this series of measurements, or lots of geophysical examples like sunspots or energy measurements, really from anything. So if you're measuring the number of or the intensity of photons coming from a certain point with the camera, that's a time series. So it's usually physical, but when you sort of plot that out with the x-axis being time and the y-axis being whatever measurement, that doesn't always give you a really good indication of the behavior that you're trying to measure. So if you think that you have a periodic signal, like you would if you had wave heights, then we have our Fourier series that we know we can approximate it with. And so this is what we've seen in the last couple sections. We have a signal and we can express it in terms of sines and cosines. And we even know how to calculate those coefficients. So I'm not going to get into the math a whole lot in the next couple slides. I'm going to show some math that you haven't seen before, probably, but just sort of show it for your awareness. We're not going to go crazy with it. So the complex Fourier series is what you really see more often when you do Fourier analysis. So instead of writing it in terms of sines and cosines, you can write sines and cosines with the e to the it. And then you get coefficients going sort of in both directions, from negative infinity to positive infinity. And if you've heard the term Fourier transform, what that is, that's sort of like the Laplace transform, where you take a function and then it gives you some other function. And in this case, the Fourier transform would take your function little f and return to you your the sequence of coefficients that come from the Fourier series. And if you generalize that to continuous k, instead of saying just k equals 0, 1, 2, 3, negative 1, negative 2, negative 3, you can make this, you can define this for any k on the real line. And so instead of having an f of t, you get this new function, big F of k, where k is sort of your frequency space. So it's just, now it is really just like the Laplace transform, where instead of having a function in t space, you have a function in what we call k space. So here's an example plotting the Fourier series, or the Fourier transform. So on the left, you have the signal that's typed up in the first line, this sine 200x plus sine 400x plus sine 600x. And it's this periodic function because it's sines. And so maybe this represents wave height, something like that. And when you look at it, it's really noisy, and, or it's not, I mean, I guess it's not noisy, but there's a lot of stuff happening over and over again, and it doesn't really give you a lot of information about, it doesn't necessarily give you all the information that might be helpful. But if you plot the Fourier transform, it's basically just giving you the coefficients of how you would break that function down into sines and cosines, which we can see. I mean, obviously our function is already broken down into sines, and we can see the what in the terminology we used in the book would have been like the CN for n equals 200, n equals 400, n equals 600. And just because of math details, we end up sort of dividing those frequencies by 2 when it gets plotted. But you can see that instead of having sort of this noisy signal that goes over and over and over again and gives you really more information than you need in some ways, it's telling you, hey, there's a spike at 100, a spike at 200, and a spike at 300. And that's a much cleaner sort of thing that you're not seeing in the regular time space on the left. And so that tells you, instead of saying, well, the wave's happening over and over and over again, it's telling you how often the waves are happening, that there's something happening every 100, and then something happening every 200, and something happening every 300. You can also, by breaking things apart into different frequencies, you can filter out the higher frequencies or separate a signal. So one of the big challenges in signal processing is called source separation, where you have 2 different signals happening at the same time and you want to isolate one or another. So for example, if you have a conversation happening with a bunch of background noise and you want to get rid of the background noise so that you can hear just the conversation, if you can figure out which frequencies the noise is happening at, then you can just sort of say, don't show me those things, only show me the things that are happening at the frequency that I care about. And then you can also look at sort of energy that's coming in at a particular frequency. And so there's like tons more on this that you would see if you ever took a digital signal processing class. And there's lots of sort of technical difficulties with computing that Fourier transform. And there's some interesting sort of computational history there in the development of the fast Fourier transform, which is the algorithm that is commonly used to compute this. Because usually you have to, I mean, if you remember, you have that sort of infinite integral, and so you have to estimate things in certain ways and do them in a way that's not going to lose information or introduce information that you don't want to have. All right, so I think that's all for signal processing because it's not really my area, but I sort of wanted to show you what the Fourier transform can be used for. Now, I wanted to give a bunch more examples of image processing, but I didn't actually want to take the time to put them together. So I found a short YouTube video that I'm going to play. It's like 5 minutes, but it's going to be super janky right now because I can't share the audio on my computer. So I'm going to use another device to play the audio. It's going to be a little complicated. So bear with me. And if you are having any problems like hearing, if you're not hearing the video or anything, like, I don't know, shout out and we'll try it again. So 1 second.
One of the tools that we use in image processing is the Fourier transform. The Fourier transform is an extension of the Fourier series, which we use for periodic continuous signals. The Fourier transform can take care of non-periodic signals like this white noise. One of the things that we are often interested in with image processing is reading text. The fact is that while humans are very good at reading handwritten and printed text, computers really struggle with it. This is the reason that some websites use these capture images. These allow the website to make sure that it is dealing with a real human instead of a computer or a robot. Having a computer read text is useful for the post office, for transferring books to electronic copies, for number plate recognition, and for automating the input of handwritten forms. One of the methods that is used for recognizing characters is to use the Fourier transform. When we apply a transform to something, we retain the information that is captured in the original data, but we display it in a different way. It's the same as taking these waveforms, which are displayed in Cartesian space, and displaying them using a log scale instead. All the information is still there, it is just easier to interpret it in this new form. If we take the Fourier transform of a signal, we move it from the time domain to the frequency domain. A step function in the time domain becomes a sinc function in the frequency domain. If we move back to the time domain, you will still get back to the original data. As a quick aside, the sinc function in the time domain becomes a step function in the frequency domain. But a word of warning, it doesn't work like that for all signals. We can also move images into the frequency domain. This image of parallel graduated lines becomes two white dots on a black background in the frequency domain. This white circle becomes a pattern that looks like ripples from a stone thrown in the water. And this white square on a black background becomes a cross. The more you look at the patterns in the frequency domain caused by these simple shapes, the more you can predict what might happen if you change the design. For instance, if I change the spacing between the graduated lines, the dots in the frequency domain move apart. And if I rotate the lines, the dots rotate as well. We can also take the Fourier transform of more complex images. This image is very famous in the image processing community, and here it is in the frequency domain. The lines in the frequency domain image correspond to the legs of the tripod and the line of the horizon. What researchers have found is that we can actually exploit the lines and circles and their corresponding patterns in the frequency domain to use it to recognize characters. Let's look at the letter A, for example. Pretty much however you draw it, it has two upright or close to upright lines and a crossbar at the bottom. When we transfer these to the frequency domain, they all end up looking quite similar. And they definitely look more similar to one another than the B, or a C, or a D. In fact, we can use the representation of written numbers and letters in the frequency domain to identify what letter or number is in the time domain, and so we use the Fourier transform to identify letters and numbers. We can also use the frequency domain to remove noise from an image. For instance, in this case, the image has been corrupted with diagonal lines. These lines appear as very bright spots and circles in the frequency domain, so we can remove them using a filter. This is the filter applied, and this is the image with the noise removed. We can also remove white noise or speckle by removing the low frequency components of the signal in the frequency domain. These sit at the extremities of the image, so we only keep the signals in the middle. This is the filter applied, and this is the result. While it may look a bit blurry to you and I, there is now no noise, so the computer can make better judgments about the image. I've only shown you a few examples, but you can see from this short presentation just how useful the Fourier is for image processing and analysis.
All right. So it's annoying that there was that one image that was removed for copyright purposes, but it was really that cameraman example that I wanted to show, because that's one of the sort of classic problems in image processing is noise removal, is removing that high frequency noise. And what happens when you remove the high frequency, you end up blurring the image. So that's a problem that we'd like to try to address in some ways. So let's talk about another interpretation of how to remove noise from an image. And then we're going to talk about a way to try to remove noise from image without doing so much blurring. So we've got our heat equation, which we've seen in the last couple sections. And when we solved it, we used our eigenfunctions, and we get our solution looks like our sort of exponential functions. I don't know if you can see my cursor, but I'm pointing at the exponential functions, and then our sine functions. And in this case, we're taking our initial condition to be just a single hump of a sine wave. And so in order to, so we can solve for these CNs by figuring out what the sort of coefficients are of the sine series representation of our initial condition, which is just, you know, we've only got one sine term. So that means that our C1 is going to be 1 and all the rest will be 0. And we just get left with this function e to the negative t sine x. So what does that function look like? Well, it's just a regular sine x at t equals 0. And then as time goes on, the exponential, that e to the negative t, will sort of wear down the sine. And so for a couple different values of t, we start off with the blue sine hump, and then at t equals 1, 2, 3, and 4, we start smoothing that sine down to 0. And that's sort of what would happen with any solution. If we go back to what our solutions look like, we have our sine waves, and for the higher ends, those are going to be really high frequency things. And then we're going to smooth all of those down because we're going to smooth them down with these exponentials. So that is equivalent to this what's called Gaussian smoothing. So if you might have seen the smoothing operator in like Photoshop, there we go. It's basically the same thing as evolving a heat equation. And the physical interpretation of that is that you have, imagine lighting a match in the middle of the room. You're going to have this high, at the very beginning, you'll have this high spark of heat right in the middle of the room. And then as time goes on, very quickly in that case, all of the heat will sort of dissipate throughout the room, and everything will go to just a constant temperature without any additional heat sources going in. And so that's why it makes sense from a physical perspective to use the heat equation to model a smoothing operation. And so the exponents, like back in the solution, this e to the negative n pi over L, those are going to be faster, like faster exponentials, or they'll die off faster for the higher n. So for the higher frequency terms, those will smooth down to 0 even faster. And so that's why if you just sort of take your image as the initial condition and then solve the heat equation with that initial condition, that will give you the smoothing operator by killing off those high frequency things. And if you take time for long enough, you'll end up with just a solid gray image that would be the like the average gray value of the whole image. So that's what I said right here. So if you, yeah, that's exactly what's said. Okay. So let's think about another reason that this works this way. So let's go back and look at our equation. We've got our heat equation is du dt, which in the next image or the next graph I just write as ut, and equals uxx. So the first derivative with respect to t equals the second derivative with respect to x. Okay, so if u is our function, if u is concave down, that's the same as saying that uxx, the second derivative, the second spatial derivative, is negative, right? So that's this sort of downward facing hump in our image. And if u satisfies our our PDE, then uxx equals ut. So now ut will also be negative, and that means that that u is decreasing. So we're going to be like sort of smashing that down. And then contrary, if uxx is positive, then so is ut. And so now your concavity will be sort of smoothing up. So those are just like a couple different ways to interpret the same behavior from this equation. Okay, so now let's think about how to apply this to image processing again, and think about how we can get rid of some of that blurring behavior. So now that we're talking about images, we have to think about the situation where we have two spatial derivatives. So instead of ut equals uxx, we're going to write du dt. We still only have one time dimension because there's only one time dimension. And that's going to equal, instead of like the way that we represent the second derivative in both dimensions, is we do uxx plus uxy, or sorry, I said that wrong, uxx plus uyy. And that expression is equal to this sort of delta operator here, which is called the Laplacian operator. And it is really annoying that it is written with a delta because we use deltas in other places, but that's just what it is. And you need to understand what it is from context when you're actually working with it. So that's how our equation ends up looking. Let's see. What else do I want to say here? Okay. So our initial condition is an image. So again, let me go back here. So now we're going to be in two spatial dimensions. So we'll have our extra uyy up in the first line. And then we have our whatever our conditions on t are. We'll actually talk about that in a second. And then our initial condition, we're saying when time equals 0, we want the initial image that we're starting with. So that would be u of x comma y comma 0. So it's an image that doesn't change in time, but has x and y dimensions. And that'll be some function. And you can think of an image as a function because you have, if you think about each pixel in it, that gives you your sort of xy coordinate. And then for every x comma y, you get a pixel, and then you give it a gray value or a RGB value, depending on how you want to do it. But if you think about a grayscale image, it's just a function from the x and y coordinate to the grayscale value at that pixel. And then if you want to code this, then you have to, so we're going to, put the image into our, computer, and we have to represent the derivatives numerically somehow. And I'm not going to go into this a lot because it's a really hard thing to just read off. I don't know, I don't like this stuff so much, but we talked about numerical approximations a bit, in the before times. And these are just a couple different approaches that you can take to approximating these derivatives to do these approximations. So our du dt is sort of a simple one. We can just say, well, at a step forward in time minus the current time, we've got or divided by the time step. And so if we plug this into our heat equation, if we replace the left-hand side, the du dt, with our approximation, then we end up multiplying the Laplacian by our dt. And now we have to approximate the Laplacian somehow, those spatial derivatives. And with this one, we end up doing a central finite difference. The reason that we're going to go forward with our time derivative is because our time is only moving forward. But with the spatial derivatives, we sort of want things to be happening even on either side, because we don't necessarily favor right or left or up or down or anything like that. And so now you sort of take your point and do your difference limit, like split the difference between right and left. And you get these things, you have to do it twice. And so you get our h is the step and blah, blah. And then there's some MATLAB code that I wrote like 4 years ago, and I'm not going to try to explain, but it's really not that complicated to sort of start estimating these things. You just, you know, sort of figure out what your approximation should look like, and then just, you know, take your vector of points and do those operations and plug it in. All right, so that's how you do it. Or you look it up and find someone else who's already done it and then plug it in. Copy and paste from Stack Overflow. Okay, so the problem that we talked about before that you saw in the YouTube video is that if you remove that noise, so equivalently moving forward, solving the heat equation and taking that solution as your like new image, the solution at some positive t as your new image, or by filtering off the Fourier coefficients in the Fourier domain, then you will remove the noise, but it will blur all of your edges. So what can we do about that? And the answer is that when the gradient is high, so that would be where there's a steep shift between the grayscale values. So like if you have a white region next to a black region, then the gradient between those two would be very high, like if you had a checkerboard. If you think about what would the gradient, and the gradient is just the derivative in the x or the y direction. If you had a checkerboard image, your derivatives in both x and y on either the white squares or the black squares would be 0, because you're not moving anywhere, you're not changing intensity. But right at those edges between the squares, so now the difference between the values on the white squares and black squares would be very large. So your derivative would be high. And the gradient is just sort of this two-dimensional generalization of a derivative. So whenever you have an edge, your gradient is high. And in fact, you sometimes use, in image processing, you use a gradient as an edge detector. You sort of take the gradient of the whole image, and it gives you just the locations of those edges, so that you can use that to you know, detect objects, that sort of thing. Now, we want to slow down the diffusion when that gradient is high. But how do we slow down the diffusion? So let's take our equation, du dt equals the Laplacian of u. And if we just plugged a number in before the Laplacian, that would change the rate at which we're going to diffuse, that we're going to smooth things. And so if our a is greater than 1, if a was like 100, then our ut, our du dt would be bigger, right? And so everything would be happening faster. And conversely, if our a was like really close to 0, then it would slow things down. So if we stuck an A in front of the Laplacian, it would be like the same behavior, only faster or slower. Now, this is the rest of the equations on this line are like different ways that you can express that. So because A is a constant and the Laplacian is just derivatives, you can pull the constant inside these parentheses here. And so saying the Laplacian of AU equals A times the Laplacian of U. That one's kind of obvious. This last one is not terribly obvious, especially if you don't even know what this upside down delta is. That is called a nabla, and it's the symbol for a gradient. So what this is saying here is the gradient of A times the gradient of U. And so without getting into all the details here, the gradient of the gradient, this is like the first derivative of the first derivative, and that equals the Laplacian. So upside down delta equals right side up delta. And so you could sort of stick this A in the middle of the two. And that might seem like a really weird thing to do, but it makes sense for other reasons that we're not going to talk about here. So just sort of suffice to say that these are all equivalent expressions. Okay, so if we plugged like an A in here, we could speed up the smoothing or we could slow it down, but we'd still have blurring because it's going to speed everything up equally. So the idea is that we want A to be small where we have edges. That would be at, I don't remember what I was just about to say. So if we have think about the checkerboard example. And let's say that we added a bunch of noise to the whole image. So in the middle of the squares, we want A to be 1 or bigger. We want the regular kind of smoothing. Maybe we even want to speed up the smoothing. Where our gradient is 0 and everything's flat. There's going to be this high frequency noise that we want to get rid of. And so we'll smooth everything away. But at the edges, if you blurred a checkerboard, then those edges would get blurry right away. And so where that gradient is high, we want to plug in an A that's really small. So we're going to, instead of making A a constant, we're going to make it dependent on U. And in fact, it's going to be dependent on the gradient of U. So we make it this G of the gradient squared, and we square the gradient for reasons. And G might be some function like 1 over 1 plus x, which I've plotted here. So if the gradient is large, if you're way on the right side, then G of the gradient is going to be really small, and you'll have slow diffusion. Whereas if G is very small, if you're in the flat regions and G is close to 0, then or if your gradient is very small, then G will be very large, and you'll get fast diffusion. And this is called anisotropic diffusion, in contrast to the regular heat equation, which would be called isotropic, iso meaning that it's the same everywhere, and anisotropic means that it's not the same everywhere. And so this is the idea. It was first published by Perona and Malik, who were two, they continue to be two really big names in computer vision and image processing. And if you have your gradient is very small, then we're going to have a lot of diffusion and get smoothing in those areas. And if your gradient is very large, then you'll slow down your diffusion. And this is the equation that you end up with. So we have our ut, and then instead of writing Laplacian of u, we're going to break this up with our gradient dot. Now, instead of a, we plugged in our g of the gradient, times our gradient of u. Our boundary conditions are a little bit different than we saw before. And what this boundary condition means is that it's sort of like the derivative. This is basically saying that the derivative of your image at the edges is 0, because you're not changing as you go across the boundaries. Yeah. And then our initial condition, u at, I should have put an x there, u at x comma 0 or x comma y comma 0 equals your u0, u0, which is your initial image. And so the problem that we get here is that now that we've plugged our g in here, which is this sort of nonlinear function that depends on the gradient, now our whole equation is nonlinear. And we know nonlinear is hard. And we know that we have ways of solving the heat equation when it's linear. But now that we've thrown this weird behavior into it, we don't necessarily know how to solve it. And in fact, you can show that this equation doesn't have a solution. And that doesn't stop you from using it. You can, even though this equation doesn't have an actual like sort of analytic solution, a mathematical solution, you can still do the approximation. And like I showed before, you can do those forward difference and central limits and everything, and plug it into your computer. You can do whatever you want. But you end up with some sort of unstable behavior sometimes. And you can sort of show that when you use this equation, you might get some weird behavior happening at places where your edges are really steep, which is exactly where you don't want to get that. And so there is a body of literature on how you sort of maybe tweak this equation a little bit so that it still has the anisotropic diffusion behavior that you want, but also has nice mathematical properties so that things will be a little bit more stable. And so that's sort of just the beginning of how you start using these differential equations for really any type of application. And that is it. I stole this XKCD comic from that video. It's now my favorite comic. It is really stupid, but I love it.